Pressure. We started pressure last week, and we have gone as far as talking about atmospheric pressure. Do we have any question posing problem to us? If you have, I will welcome one or two before I proceed. And if you don't have any, I will proceed straight. But like I said earlier, it's expected of you to lay hands on past questions. Last class, I made mention of JAMB Remix. Remix has a question on various topics, which I think can help you to at least to test your knowledge on every topic that you have there. So, if you have one or two questions on what you have done, or you have questions generally, it may not be the topic we have done, you have a question that is posing problems to you in physics, can I have one or two before I proceed? I'll be ready to respond or to contribute to the solution of the question that may be given to us. Somebody, how many have questions? Only one. Okay, let's quickly have your question and we'll proceed. If I see you talking, you will remain standing here till the end of the class. Please have to put some forward. The fast. That boy, you stand up. Abel. See looking at back. Stand up. A gas with initial volume of 2 times 10⁸ meter cube is allowed to expand to 6 times its initial volume at constant pressure. At constant pressure of 2 times 10⁸ per meter, the work done is, yes, what is the work done? If you have this type of question given to us, who wants to try it? Anybody? The question is, a gas with initial volume of 2 times 10⁸ meter cube is allowed to expand to 6 times as initial volume at constant pressure of this. Gas pressure of 2 times 10⁸, the work done is that. Anybody? No direct solution. You have initial volume. U is 2 times 10⁸ meter cube. Final volume V is 6 times U, which is 6 times 2 times 10⁸, and that is 12 times 10⁸ meter cube. The constant pressure P, is 2.0 times 10 raised to the power 8 Newton per meter square. Then we need work done. Work done, WD, not known. But you should know that work done, you know, is pressure times volume. Pressure times volume. But the volume now changes. So it will now be delta V. So what is delta V all about? You have pressure into V minus U. And if you have V to be 6U, P into 6U minus U. And that will give you P into 5U. What is your P? Your P is 2 times 10 raised to the power 8 Newton per meter, then times 5 times 2 times 10 raised to the power 8. Then 2 times 2, that's 4. 4 times 5, that's 20. 20 times 10 raised to the power 8 times 10 raised to the power 8. By indices, you have 20 times 10 raised to the power 8 plus 8. That's 16. 2.0 times 10 raised to the power 17 joules. By the time you use dimension, this pressure is Newton per meter square times meter cube. The square will cancel this. What will be left will be Newton meter, which is dou. But the only thing is, your initial volume was this. It expands to this. So change in volume times the pressure will give you the work done you want to. Sit down. Now the atmospheric pressure we want to discuss today. Here's the duster. I did not hear you.
The pressure exerted on every particle in the atmosphere.
Okay, pressure exerted on every particle in the atmosphere. Not exactly. Who else want to contribute?
Exerted on every particle by the atmosphere.
By the atmosphere, that is fear, that is better. Yes, you want to say something? Okay, what do we understand by atmosphere? Maybe that would be a bit, yes. Talk to the class. When it's time for you to talk now, we force you to talk. But if it is murmur, nobody will ask you to do that before. Can you hear him there?
Atmospheric pressure is pressure exerted on the body by the constituent elements, the particles of
Okay. But I haven't left the atmospheric pressure. I was asking about what do you understand by the atmosphere. Well, to save our time, all these things, that's why we say physics is physical, what you see. Forget about how it is defined in your textbook or in your school. What do you think atmosphere is? What do you know about the atmosphere? Any other person? Yes?
Atmosphere is the mixture of gases around us.
It's a mixture of gases around us. You have at least what we know is gases are not visible. But it is certain that you breathe out some gases, which of course the plants around you make use. Plant also releases some gases to the atmosphere. Aside this, the water vapor from the ground goes to where? To the atmosphere. The particles go to the atmosphere. Here we all know it's a mixture of gases. All this occupies, all this fill up the atmosphere. This one, by the definition of matter, which we know to be anything that has what? And do what? So, when we say anything that has mass and occupies space, it means the air or the gases we are talking about, they occupy space and they have their own masses. That masses they have are above us. They are above every object on earth. And by the time you convert those gases, the mass of those gases to their weight, that weight is upon something. The weight of the gases above us, the weight of the water vapors above us, the weight of the particles, and some other things that are in the atmosphere presses every object, either solid or liquid. Atmosphere exerts forces on us, and the force, which is the weight of those gases exerts on us, is exerted on certain area. Your area now, the pressure is on you. We defined pressure last week as force per normal area. So if you have weight, and weight is acting on, so you can convert that weight, which is the force, to pressure. All you need to do is to divide the weight by the area in contact. That's what we discussed last week. Even the atmospheric pressure, I started it last week. So when we are now talking about atmospheric pressure, we are now talking about the pressure the atmosphere exerts on us. So the atmosphere exerts pressure on every object, be it solid or liquid. If you fetch water into a bowl or a cup, the bowl or the cup is exposed to the atmosphere, and it means the weight of the gases will act on the surface of that thing. It will exert pressure on it, and that pressure is called atmospheric pressure. Is that taken? And that's the reason you have so many evidences to show that we have atmospheric pressure on us. Look at some container or the ball. If you inflate the tires or the ball, you pump gas into it, it spread. By the time you pump out the gases in the tube or the football or whatever, the ball will not remain as big as it was when the gas is inside. It is the atmospheric pressure that will press it down, that will make it to be flat as it is. So, and so many other things you can see around you that actually show that we have pressure on us. We have atmospheric pressures on us. Now, having said this, what is the instrument that can be used to measure atmospheric pressure? I think I mentioned it last week. Barometer, yes. Barometer, we have different types of barometer. But even if you know, barometer is a device that can be used to measure atmospheric pressure. And who can describe the barometer we are talking about? How does barometer, simple barometer, simple one. Who can describe it? Or how many of you have seen barometer before? A simple barometer consists a long 1 meter rule, a 1 meter long glass tube, 1 meter long narrow glass tube. That means a glass tube that is 1 meter in length. Then you need a reservoir. Then you need mercury. These are the simple components of simple barometer. A meter long narrow tube, glass tube, so to say. Then you need a reservoir, and you need the liquid called mercury. So what do I mean? I mean we have a narrow tube like this, which of course is a meter long, Then you need a reservoir, a container like this. Then you now need mercury. You pour mercury inside the reservoir. This is the mercury inside the reservoir. Then this is the glass tube, a meter long glass tube. If you want to do this, you need to wear hand glove. The hand glove will be what? And you have fill this tube to 3/4. What's 3/4 of a meter long? A meter is 100 centimeters. 3/4 of it will be 75 centimeters. So you fill this to roughly 75. You fill this with mercury. You fill it to 75 mercury. This is the mercury inside the reservoir. Then with the hand glove in your hand, with the hand glove in your hands like this, cover the end of the tube and jack the tube several times. Jack. That means you invite, you turn it back, you invite, you turn it back. You jack it for some time. Why do you need to jack it? Can someone tell me why it should be jacked? Can someone tell me why it should be jacked? Yes. To remove the air bubble that might have been trapped when you are pouring the mercury into the tube. No matter what you can do, you have some trapped air inside. And by the time you jack it severally, the air bubble will come to the top here, and then you can now fill it to the brim. You later fill, after you have jacked for some time, you pour mercury to fill it up to the edge of the tube to fill the remaining. So if this is done, cover the edge and carefully bring it down and invite it into the reservoir here. And what we will notice is that the mercury will drop the height down. This is exactly what we observe. Meaning that what you have above is an empty space. Nothing is there. If you did not jack it before, if this was not jacked before you turn it down, then some of the bubble, the air bubble, will run up here and constitute nuisance there, constitute pressure. That is, the gas, the air bubble will go to the top and exert its own pressure together with the pressure of the mercury above. But since this place is empty, nothing is there, then we believe that the only pressure we need to know is the pressure due to the level of this liquid, mercury. And the atmospheric pressure we act here, atmospheric pressure we act here. So this is AP, atmospheric pressure, AP, atmospheric pressure. This atmospheric pressure, we have the same pressure at this level, which is the same level with this side. The pressure here equal to the pressure here, equal to the pressure here. So if you actually want to know the pressure, atmospheric pressure, which is here, you calculate the pressure here. If you now measure from here to here, that gives us 76 centimeter high. So from this level to this height, we give you 76 or 760 millimeter Hg, mercury. That's the height that will be given to you. And we believe it is the atmosphere that sustains that height. It is the atmosphere that sustains that height. And that's the reason why we usually say what is atmospheric pressure. Atmospheric pressure is 760 mmHg. It only gives the equivalent height. It gives the equivalent height of the pressure. So the atmospheric pressure will sustain the height of 760 millimeter mercury, which can be converted. If it were to be water you use, the height of the water will be so high that nobody can, it will not be easier to use glass tube as long as that. Now, what do I mean? The atmospheric pressure, as we said, has the 760 mmHg. If you want to convert it to actual pressure, atmospheric pressure is equals to height of the mercury, density of mercury times G. Height is given to be this now, 0.76. Density of mercury is 13,600 times 10. That is the atmospheric pressure in mercury. If you want it in water, then you can convert it to water. If you want atmospheric pressure, what is going to be the height of it? If water were to be used, then what we will say is AP equals H of water, then density of water times G. So atmospheric is this, 0.76 times 13,600 times 10 equals height of water we don't know, but we know density of water to be 1,000 times 10. So height of water now, if water are to be used, height of water will then be equals to 0.76 times 13,600 times 10 all over 1,000 times 10. So this will cancel this. 20 cancel 20 here. Then you have 0.76 times 13.6 equals H of water. So if you are to be the water we use instead of mercury, this will be the height. What is 76 times 13.6? What is it? 103.6. So it means we need 10.3 about kilometer. The height of the tube will be about 10.3 kilometer, 36 or 336, which is very, even if you say 10 kilometer, you know what a kilometer is. And so it will be so long that we cannot, such an instrument or device cannot be made. So, yes, whatever it is, get it. What we are saying in essence is the height of the water will be so long, longer than that of mercury. Is that clear? So we are going to come across so many questions that involve the pressure like this, especially when we are talking about atmospheric pressure. And please, I said 760. The examiner may be funny. Whatever you are given to be used as atmospheric pressure, that's what you should use. Some questions, they say, take atmospheric pressure to be 70 centimeter Hg. Do not say it's not 70. You are using 76 centimeter. You are wrong. Density of mercury used to be 13,600. Some other may give you use 13,800. Whatever the examiner asks you to use, that's what you are going to use, because that is what the examiner used to work out the answer. Is that taken? Yes. What is important for you to know? The concept you need to know, not the final answer that is matter, but the concept is how do we convert the height to pressure. One, what is atmospheric pressure? Then the height of it. Every other thing is simple mathematics, and you are allowed to use calculator. So don't base what your argument or whatever on that. Yes, this is the answer. Hey, this is not the answer. The concept matters most. I have told you what to mark in calculation. Now, having known this, the calculations, how to convert height to pressure, how to read barometer. What we read in barometer is the height. Once you get the height, you can convert that height to pressure by using H rho G. That is the formula for the pressure. The next thing is to talk about gas pressure. Gas pressure. That's the next thing. The gas pressure, just as you already know, gas or gases also exert pressure. How do we know the pressure exerted by the gas? Or how are you sure the gas exerts pressure? Of course, each molecules of the gas are not just stationary in the cylinder. The molecules are moving about like a ball. The molecules are moving about like balls in the cylinder, and they make collision with each other and with the wall. The time rate of collision, the number of collision per second, determine the pressure exerted in the gas. That means the rate at which each molecule collides with the wall determines the pressure exerted by the gas on the cylinder, the wall of the cylinder. It means the number of collision per second determine. If the speed of the gas increases, the rate of collision will increase and the pressure will be very high. And if the speed remains the same, the rate at which the molecule collides may not change. But you should know that the rate at which each molecule collides with the wall brings about the pressure the gas exerts on the wall and of course on each other. Now, how do we know or determine or measure the gas pressure? The only device that can be used to measure the gas pressure is called manometer. We have the first one we talked about is barometer. Now we are talking about manometer. And we have two types of manometer. We have two types of manometer. We have mercury manometer and we have water manometer. We have mercury manometer and we have water manometer. The mercury manometer consists of mercury. A manometer is a U shape with one arm longer than the other. Of course, when you write U has two arms. But manometer will have one longer, one of the two will be longer than the other. That means one long and one short arm. So it all depends on what liquid is poured inside that will give names to the barometer. Is it mercury that you pour in? Is it water? So a manometer is made up of U shape. This is U. You have U shape. Then this one arm will be longer than the other. So you can reduce this one to make your manometer. And this will now be connected to gas chamber. You can connect this one to gas cylinder. You already constructed your manometer. This is a manometer. Two arms or limbs, 1 and 2. Now, if you pour mercury, you can have mercury like this. Yes, this is one position. The gas chamber, you have this one as gas chamber or chamber. Now you have this one. This is gas. Exact gas pressure here. The pressure of the gas is exerted here. So here, this is open to the atmosphere. You expect the atmospheric pressure to be here. This is AP. The level of this, the pressure here, which is the gas pressure, the pressure from the cylinder is exerted here. Once you know the pressure here, that is the pressure in the chamber here. So how do we calculate this? How do we calculate this? It's so simple. What you do is to determine the pressure at this point. How do we determine the pressure at this point? You need to know the pressure due to the level of the liquid above. That will be pressure of the liquid. Then above this liquid you have atmospheric pressure. That simply means that at this level here, the pressure you are going to have there must be addition of the two pressure above. Atmospheric pressure above, pressure due to the level of the liquid above. That will give us the gas pressure we have here. We are having gas pressure here, and it's going to be the sum of atmospheric pressure and the pressure of the liquid above. So we need to know what is the height of the liquid here. We need to know what is the height of the liquid. So if that is HL, then it is, this is mercury. We call this one mercury manometer. We have mercury manometer. Don't forget, atmospheric pressure is easier measured in terms of mercury. Atmospheric pressure is easier determined in terms of mercury. So, and what is inside the manometer is also mercury. It makes your work easier. So the height of atmospheric pressure you already given maybe 0.76. Whatever may be the height of this, convert that to meter. It will be easier for you to add the two together. HL in meter. Then will now be the total pressure of the gas times density of mercury times G. That means if you're actually looking for the pressure. So that will be the pressure due to the mercury above this point plus the atmospheric pressure above. We now give the pressure the gas exerts on this surface. And that pressure comes, you know, gas is inside the cylinder here. So you can say gas cylinder or chamber here. The pressure inside it can be exerted here. And we can only determine it by finding the pressure due to the level of this plus atmospheric pressure. If this is mercury manometer. Now, it is also possible for the height in the longer limb or the longer arm to be shorter than the mercury in this short arm. It is possible to have mercury here lower than this. And the top position is for them to have the same level. These are three possible positions you can observe in a manometer. Let me exercise the time. The mercury manometer we have mercury thread in the longer arm. How do we determine the gas pressure in such a situation? Now you have like this. This is another position you can have. Or cylinder. I'm seriously afraid of these sets. Another position you can have. The gas inside this cylinder or chamber you have here exerts pressure here. And if you look at this, the other arm open to atmosphere here, this is the level. It means the atmospheric pressure will be hearted. This is AP. And you need to know the level of this one to this plate. The pressure here will be equal to the pressure here. There is no doubt about that. The pressure at this place will be equal to the pressure here. And the pressure at this level is equal to gas pressure and pressure due to the level of the liquid. You have level of the liquid here, HL in this case. So how do we now know this? Since we know that what you have here is equivalent to what you have here, that means our AP is here, this will also be AP. So if you have done it well, you can say, of course, this is also mercury manometer. So at this point here, we can simply say atmospheric pressure equals pressure of the gas above plus pressure of the liquid. That's what you are going to have here. But the aim is to determine pressure of the gas. Make pressure of the gas the subject of formula. Pressure of the gas here will then be equals to AP, atmospheric pressure, minus pressure due to the level of the liquid. So therefore, we can say gas pressure equals atmospheric minus pressure due to. Here, we say atmospheric pressure plus pressure due to the level of liquid here. But here, we say atmospheric pressure minus. Please take note of this. The position of the mercury thread inside the manometer. Very important. The last position is when the thread in the two arms have equal height. And you don't have anything to do that to say gas pressure equals atmospheric pressure. When does that occur? When you have manometer. You have manometer like this. And this is connected to the chamber like this. And here you have the mercury. You have the mercury here. They are the same height. If they have the same height, just have this. So what you have here is atmospheric pressure. What you have here is gas pressure. Gas pressure and atmospheric pressure in this position, you can say gas pressure equals atmospheric pressure because the thread of mercury in the two arms are the same, the heights are equal. This is gas. These are three possible positions you can have. These are three possible positions you can have. But another thing that can be observed is when the liquid is water instead of mercury. When it is water instead of mercury, the meniscus will determine. In most cases, mercury bends up. That's the meniscus is concave like this inside the tube. But if it is water manometer, it is going to be convex like this. You have it. So that's the difference between the two. But whatever the case may be, the same way you have done for mercury is the same way you do for water manometer. This is water manometer. And the level here will bend down like this. The level here too will bend down like this for water manometer. Now, you cannot add HL to this as we did here because they are different things. Atmospheric pressure is 760 mercury. The water here is H water. You cannot add H of water to 76 H of mercury. So you cannot add direct. What you can do is to convert water to mercury or mercury to water. And if you want to convert water to mercury, what to do is to equate the pressure. Pressure of mercury equals pressure of water. So that means height of mercury, density of mercury times G equals height of water, density of water times G. G is common, you remove. So we can use this to change one to the other. This is mercury. Density of mercury equals height of water. This is density of water. We can use this to convert water to mercury or mercury to water. Please take note. The examiner may want to pull your leg. It's so simple. For instance, if this are to be water, and you are giving the height here to be 10 centimeter H2, and you have to calculate the gas pressure here, it's simple. You may be able to calculate in terms of water or in terms of mercury, that's no problem. Atmospheric pressure, you know, is given in mercury. The height here is given in water. What you need to do is, this is 10 centimeter, you want to change it to mercury. Just say H of mercury, density of mercury equals H of water, density of water. So you now substitute what you want to change to mercury. If density of mercury is given, so what you do is to say what will be the H of mercury. If density is 13600, and this is now water is 0.10 times 1000, density of water. So we now say, okay, height of mercury will then be equals to 0.10 times 1000 divided by 13600. That's what you are going to do. So, and obviously, this is 10 over 100. So you can turn it to be 10 times 10 above, all over 130. So 10 over 100, 0 will cancel 0, you have 10 times 10, that's 100. 0 cancels 0, 0 cancels 0. So that means H of mercury will become 1 divided by 136 in meter. So, and obviously, this in 1 will give you 0. In 10, you still have 0. In 100, you still have 0. In 1000 now, how many of these you have? But of course, you have seen that you have 0.00 mercury. That will now be added to this in meter, because you have converted 10 centimeter water to, what is 1 divided by this? 0.00735 meter. So in that case, I can now say, okay, this is equivalent to 0.00735 meter mercury, whereas atmospheric pressure is 0.76 meter mercury. So to calculate the total pressure now, this will now be this plus this. That will be. But if it were to be mercury, you have 10 centimeter here, 76. Convert this one to. If it is mercury, you have 10 centimeter Hg. Then that will give us 0.10 meter Hg. So what you do is to add straight to this, because it is mercury. But if it is water manometer, you need conversion by using this separation to convert it to mercury before it can be used. Is that clear? Any questions? We have more than 5 questions in new school physics. To those of you who have the textbook, go and practice all the questions you have in new school physics under this. This is JAM questions, area JAM likes to, and candidates usually mess up. You can see how simple the aspect is, but hardly you will see for JAM without having question under this aspect. If your density and relative density pressures are well known, I can assure you, if not 3, you are going to have up to 2 questions under this topic in your JAM. Now it's not left for you to practice small questions under it and bring as many questions that you may have that may be posing problem to you. The next thing we should do is to go straight to optics. We should start the optics, and that's light wave. But because of the practical we have on Saturday, next class will be electricity. I will discuss electricity and what you will also meet in the practical. But let me start briefly. Optics, waves and optics. Waves and optics, briefly. But we'll continue after practicals. That's after Saturday practical. Next week, we continue waves and optics. Now, waves. What is wave? Yes. Please clap for him. Any other submission? What is wave? The wave is SS2 work. But what baffles me in this set is that there is no question we ask. There is no topic I pick that you show that you have even heard something about it in your various school. Whether right or wrong, contribute, say something, you will all be looking like this. It can be defined as a periodic disturbance that involves transfer of energy from one point to another in space or medium without causing permanent displacement. It didn't put in space, but it's necessary. Wave is a periodic disturbance that involves transfer of energy from one point to another in space and medium without causing permanent displacement on the medium. Now, I quickly want to put that down for you. Are we writing it?
Yes, sir.
Wave can be defined as a periodic disturbance that involves transfer of energy from one point to another in space or medium, without causing permanent displacement on the medium. Without causing permanent displacement on the medium. I take it for periodic disturbance. Periodic disturbance. What do you understand by that? We said it's a periodic disturbance that involves transfer of energy. What do you understand by periodic disturbance? Anybody? Okay. How many of you have seen wave before? Wave. How many have seen wave before? Let me see your hands up. Okay, where and when? Yes? The boy at the back. The one that raise up, maybe you raise up your hand. Okay, how many of you have seen wave before? Nobody have seen it. How about you? Why do you want somebody? So how many of you have seen wave before? Yes, when and where? That's the best thing you know how to do. Your result will speak out. Yes? Water wave. You've seen water wave before. When and where? Yes? In Lagos. Bridge. This wave is what we see every day. Periodic disturbance. If you want to see wave now, you see it. Just fetch water into a container. Dip something into it periodically. Something spread. what spread as you are dipping. As you are dipping, you see something that spread out from that pond. What spread out is called waves. You are dipping because you are disturbing the particle on the surface. That will generate wave. That's why we say periodic disturbance, which involve, okay, the rain will soon start. When you have pool of water on the floor or on the road, and a careless driver run into the pool of water, what happened? Splash the water. Or not even driver, you throw a big stone into the pool of water, what happens? These are the waves. If you start dipping or dropping, something will spread from where the particle is being disturbed. What spread out is known as wave. Rope. You have a rope spread for to spread your washed cloth or wet cloth, so to say. If you take a rope, you attach the end, one of the two ends to something, and the other end is held in your hand. If you jack the rope like this, what do you see? That's wave. You see the wave. When you jack the wave, what travel along the wave is called waves. Or you fetch water, like I said, into a bowl, be it bath or bucket, whether plastic or whatever. Just dip any object you have, dip it and remove, dip and remove, dip and remove. Something will spread out from that pond. What spread out is called wave. That's wave. So, from the definition you are given, you can only generate wave by disturbing. And that disturbing causes vibration. You disturb the particle. As a result of that disturbance, it involves transfer of energy from that point. When you drop a stone into a pool of water, as soon as that stone lands on the pool of water, splashing the water with force, when the careless driver run into the pool of water, it will splash the water. The water that will fall on you or whoever is nearer to it will be painful. Apart from to stay in your body, it will beat your body and you feel the pain. These are physical things that you see. And you can use a rope attached to one end, like the one they use to tie ram or cow. They can use the same rope to beat the other person at the other end. To bajake, you can use. That means energy from your hand can be transferred to other end of the rope. That's carrying energy from where the something is being disturbed from your hand to the other ends. That's why we say transferring energy from one point to another without causing permanent displacement. When you use the rope to beat the other person at the other end, the rope will not be permanently displaced. Will it? Will it? No. Or the water you are disturbing by dipping something into it and water ripple travels. After you have stopped dipping, will the surface of water be permanently disturbed? No. So when we say what is wave, we can simply define wave as a periodic disturbance that involves transfer of energy from one point to another in space or medium without Now, if you look at the definitions, now, we can categorize wave into two categories. We can group it into two or classify it into two. Those waves that travel through space and the one that travel through material medium. The one that travel through space are called electromagnetic waves. They do not require material medium. They do not require material medium for their propagation. But we have some other set of waves that need material medium for their own propagation. Those ones are called mechanical wave. So it depends on the author. Some author will say type of wave, mechanical wave, electromagnetic wave. Some other author will say classes of wave, electromagnetic waves and mechanical waves. So whichever, what we know is mechanical waves are set of waves that require material medium for their propagation. They require material medium for their propagation. And we also have some other set of waves that do not require material medium. They travel through empty space. When nothing is here, they still travel through that. Such waves are called electromagnetic waves. So if an examiner say define mechanical wave, like what he gave us earlier is simply for mechanical wave. When you define wave as a periodic disturbance that involves transfer of energy from one point to another in the medium without causing permanent displacement in the medium, you are only defining mechanical wave. Because only mechanical wave that involve material medium before propagation can take place. So when you just say wave can be defined as a periodic disturbance that involves transfer of energy from one point to another in a medium without causing permanent displacement, what you have defined is nothing but mechanical waves, which is not general. And that's the reason why in space must be added. By the time you put in space, you have combined the two type of wave, and that's general wave definition of wave. When you say what is wave, you have to give the general. But when you say what is mechanical wave, then you can say mechanical wave can be defined as a periodic disturbance that involves transfer of energy from one point to another in medium without causing permanent displacement in the medium. Example of such waves are water waves. Example of such waves are water wave. You have rope wave. Water requires water. Water wave requires water as its own medium. Water needs medium before it can be propagated, before it can travel from one point to another. There must be medium. It is along that medium the water wave travel. When there is no water, there can be no water ripples. Am I communicating? Yes. No water, there will be no water wave. Then, when we are now talking about rope waves, rope is the medium along which the wave travel. When there is no rope, there will be no rope wave. Then you talk about sound. Sound also required air. As you see me talking in your presence, you can only hear because we have air in the room. If it were possible to pump all the air out in this room, we evacuate all the air. And I am talking the way I am talking. What you only see is you will know my lips are not stable. I am saying something, but you will not hear because the carrier of the sound energy, the carrier of the sound energy, which is called waves, cannot go from me, the speaker, to you, the hearer. So it means the carrier of the sound energy is called sound wave. The carrier of the sound energy is called sound wave. The wave has to tread. The road on which the wave has to tread is air. When there is no road, the carrier cannot go to the hearer, and there is no way the hearer will hear. I generate the sound energy. As I'm talking, I generate the sound energy. But the carrier of sound energy has no way. It cannot go anywhere. So the sound energy cannot carry, the sound wave cannot carry sound energy from the speaker to the ear of the hearer. And it's only the sound energy that will stimulate, sensitize your eardrum. It is the sound energy that is carried by the sound wave to your ear that will enable you to hear what the speaker is saying. When the carrier, which is the wave, cannot go, you won't hear anything. So what do I mean? Waves are carrier. Carrier of what? Carriers of energy. It depends on which wave are you talking about. If you are talking about water wave, It means water wave carries water energy. From where it is disturbed, carry that water energy to other place. Rope waves carry rope energy from the point where the energy is applied to other parts.